Okay. So for question number 2, we have, what are polar and nonpolar covalent bonds? So this is more of a conceptual questions. It's not asking you to identify anything, just asking you what they are. What are polar and non-polar bonds? Okay, so for this question, okay, we're going to actually get the help of what they answered with. Okay, the important part I'm going to highlight right away is the electronegativities, okay? Because they're not talking about polar or non-polar molecule, okay? They're talking about the bonds. Finding out a polar or non-polar molecule requires a little bit more work, where you have to really get the bonds all together and get the visualization and see if there's an imbalance, and they can identify this is a polar molecule or not. Now, just to identify the bonds, that one is specifically about the electronegativities as I've highlighted, okay? Specifically the electronegativity difference. Electronegativity difference, okay? That is what we're using to find out what polar are and which ones are polar or non-polar bonds, okay? So I'm going to break it down the different cutoffs for each one. So typically, when your electronegativity difference, okay, we're going to call that ED. So ED is less than 0.3. That is going to be non-polar, okay? When your electronegativity difference, okay, so we now have between 0.3, okay, and less than 1.6, that is going to be polar. And now 2.0, if it's greater than 2.0, that means it's ionic. But that one's a little bit tricky. I'm going to add an asterisk to it, because anything greater than 1.6 and it's a bond between a metal and non-metal also counts as an ionic bond. So just make sure you have to watch out for that, because there are quite a bit of variations between them in regards to that. So now with that being said, you're probably wondering, what does electronegativity difference mean? So the electronegativity difference, or just electronegativity, is kind of like its affinity towards electrons, okay? So you'll see when you look at the periodic table, typically the relationship, if you go look at the periodic table like that, the relationship for the electronegativity goes kind of this way, with fluorine right here being the highest one, and I think it's like radon being the lowest electronegativity. So the reason being because, well, let's start with noble gases. Noble gases, they're content with the amount of electrons they have, so they don't really have an affinity towards more electrons, so that's why they're not really counted. But fluorine, exactly, it really wants another electron. Like, that is one of its almost primary purpose. It will always try to take away electrons from other places and other atoms. And radon, on the other hand, actually really doesn't care if it has one. In fact, would want to, as easy as it can, just give it away. Like, it has no affinity towards it. Looking at the periodic table, you'll see here exactly. We have, so it's actually francium, not radon. So francium, radium is right here. Francium is the one that has the lowest electronegativity of 0.7, and fluorine has 3.98. So as you're calculating the electronegativity difference, what you do there is you subtract the lower number from the greater number and see what you have left. You can do it other way, but you have to make sure you get the absolute value, because electronegativity difference is always done in its positive value. That's really the only way it makes sense. And then you're able to see which criteria it falls under, whether it's non-polar, polar, or ionic. Because the question is talking about polar versus non-polar covalent bonds, this would be the difference here. It would be the electronegativity difference, specifically between the ranges, well, 0.3 serving as a cutoff. Less than 0.3 is non-polar. Greater than 0.3 is going to be polar or maybe ionic later on. But yeah, And just as how it says here, I'm going to touch base on even what it means to be nonpolar versus polar. So nonpolar would be when there's no, I guess when there's little electronegativity difference. It means that they both have around the same affinity for electrons, which is why the electrons will be evenly shared amongst them. For polar, before we get to ionic, one side would just will have the higher concentration-ish of electrons, as in the electrons would prefer to hover around there more, the one with a greater value. If the difference is enough, the electrons would actually prefer, or specifically the atom itself would actually prefer to have more electrons surround that atom. Okay, so as they show here in this example, CH4 methane is a nonpolar covalent bond because actually the difference in electronegativity between carbon and hydrogen is actually like almost around exactly 0.3. Okay, so that's why we don't count that. Let me just double check here. We have, or is it 0.4? I think it's 0.4 as a cutoff. There we go. Because you'll see here, C and H is, you have 2.55 and 2.20. Yep, 0.35. Yeah, it is 0.4. So, in fact, even when we do this, I would always check with your instructor, because they do have specific rules they follow, like this whole polar versus ionic. Just make sure that whatever notes you're giving, you follow that, because that should answer what is determined as a polar or non-polar bond. Okay, so CH4, that is non-polar. H2O, the electronegativity difference there is actually quite drastic. So oxygen has the electronegativity of 3.44, and hydrogen is still 2.20. So it's like 1.24 difference. So it definitely falls in range of what we define as polar. And so the oxygens will kind of have an affinity for the electrons present between the oxygens and the hydrogens. So that is how that is a polar bond, okay? So that being said, that is correct. Let's move on to question number 3.